In this demo, we'll construct a recurrent neural network to classify images. Now, pay close attention to the tf.nn.dynamic underscore RNN library function when we use it. What is the shape of the input that it expects? So far, we've spoken of RNNs as being great at working with sequential data. Text is naturally a sequence of words, which is why RNNs are often used in text processing algorithms such as sentiment analysis, autocomplete, and so on. RNNs can work on other problem types as well, such as image classification, provided we find some way to represent an image as a sequence. And that's exactly what we'll do in this very first demo on RNNs. We'll perform image classification on the MNIST dataset using RNNs this time. The original source for this code is available at this GitHub page here. This example is from Aurélien Geron's machine learning book, Hands on Machine Learning with Scikit-learn and TensorFlow. This is a great book, by the way. The examples are amazing, the book is well written and very interesting to read. Once again, there is really nothing interesting in the import statements that I need for this particular demo. They're the same as the imports that we've seen earlier. This example uses the MNIST handwritten digits. If you're kind of bored of this, you can choose some other image sequence. But because these are RNNs, you'll find that RNNs are not great at classifying very complicated images. So handwritten digits is actually a good example to use with RNNs. Use the TensorFlow libraries to access and download the MNIST dataset. This is extremely useful, makes the process very quick. We'll once again set up our trusty helper function to display a single digit to the screen. Remember that the MNIST data that we get when we access it using the TensorFlow library is in the form of one-dimensional arrays. One-dimensional arrays of 28 by 28 pixels equal to 784 pixels in each array. Each pixel is represented using just one value for intensity because these are grayscale images. We have to reshape the input digit in order to display it as an image. We'll just use a single batch of test digits here. Here are the test digits and test labels. We'll just use 200 images. All of these are up to you. I'm just using a small sample for this demo. Test out our display digit helper function. That works fine. You can see the digit 8 on screen. Explore the test labels. You can see they are just digits or numbers identifying our images. We are now ready to set up our recurrent neural network. Set up some of the parameters that we'll use within this RNN. The first of these is the n underscore steps and the n underscore inputs. Both of these are set to 28. Now, n underscore steps represents the number of time instances for this recurrent neural network. This is also equal to the number of layers that our RNN will have. Now, why is it 28? We'll see that in just a bit. N underscore inputs represents the dimension of one input instance. So at every step, we feed in an input which has dimensionality equal to 28. N underscore neurons refers to the number of neurons which make up a single memory cell. This is also equal to the number of neurons which exist in one layer of our recurrent neural network. We've chosen 200 here. This is a hyperparameter that you can tune. And finally, n outputs is something that we've seen before. The number of labels that you can predict on our MNIST handwritten data set is 10. The labels are from 0 through 9, which is why the value of n underscore outputs is 10. In order to understand why the parameters are set up in this manner, you need to understand the shape of the RNN inputs that we feed into the TensorFlow libraries for setting up RNNs. The library that we use to build recurrent neural networks in TensorFlow expects the inputs to be in this form, to have the shape with batch size as the first dimension, steps in time as the second dimension, and the dimensionality of the input specified as the third dimension. This is a 3D tensor. Batch size is set to none because the number of instances that we want to feed in one batch is unknown when we actually set up our RNN. This should not surprise you. This is typically the case for all neural network problems that we've worked on so far. The second parameter, n underscore steps, represents the number of instances in time for which this neural network has to be unrolled. In order to figure out the number of steps in time, you need to look at the data that you have and figure out how many discrete time intervals or time steps it covers. See the number of steps for which inputs are available and set up your parameter using that information. And the third dimension of the tensor will contain the size or dimensionality of the inputs. This is the vector size which represents one input instance. At a particular time step, this one input instance is fed into our RNN. Now, when we talk about text, it makes sense as sequential data, and we can imagine that one word of a sentence is fed in at one instance in time. But how would you represent images as steps in time? You can do something tricky, and that's exactly what we've done with the MNIST dataset. You know that an image is simply a 2D matrix. Because the MNIST dataset is in grayscale, this image has just one value to represent every pixel, the intensity value. In order to represent this image in the form that our RNN expects, we need to structure the image array so that every row of an image is one step in time. Slice the image such that one row of pixels in the image is fed to the RNN at one time instant. Here, starting at time instance t equal to 0, that's when the first row of this image will be fed into our RNN. At time t is equal to 1, the second row t is equal to 2, the third row, and so on. If you remember, an image in our MNIST dataset is a 28 by 28 image, which means there are 28 rows in each image. Our RNN will be unrolled to 28 layers, which is why n underscore steps was initialized to 28 when we saw the code. The n underscore inputs is the dimensionality or the vector size of one input instance. Because the width of our image is 28 pixels, the dimensions of each input is the width of our image. The parameters that we set up in code earlier, where n steps is 28, n inputs is 28, should make much more sense now. Understanding the shape of the inputs is really the hardest part of building an RNN because TensorFlow makes it very easy once you have your input set up correctly to actually build an RNN. Instantiate placeholders for your x and y values. There is no difference in the setup here. The x values are the images that you'll feed in the shape that the RNN expects, and the y values are the numbers which are the labels for each image. Notice the shape of our X input. All our images have to be reshaped and fed in this format. The first is the batch size, the second is the number of time instances for which we have inputs, and the third is the dimensionality of a single input instance. Because we have input for just 28 time instances, this isn't a very deep RNN. That is why the memory cell that we use can be the basic cell. We don't use a long term memory cell. You can instantiate a basic cell by calling basic RNN cell in the tf-contrib library. Just one heads up here that classes in the tf.contribs page are subject to change. So if you have a later version of TensorFlow, you might find that the basic RNN cell has been moved elsewhere. So that's something that you need to watch out for. The one argument that you need to specify when you set up this basic RNN cell is the number of neurons in this memory cell. We've initialized it to 200. And here is an example of what I mean when I say that TensorFlow makes it very easy for you to build RNNs. You don't have to painstakingly connect up the various RNN layers for every time instant. You simply use the tf.nn.dynamic underscore RNN library. This takes as its input argument the cell that you just set up and also the X parameter, the placeholder where you'll feed in your training data. It'll look at the number of time instances for which it has to unroll the RNN. It'll do so automatically and wire up the connections correctly. It's all abstracted away from you. You don't need to actually do anything. Once the training data has been used to train the RNN, the result that you get is an output from the last layer and the last internal state of your memory cell. That's what you store in the outputs and states variable that you can see here on screen. Because this is a classification problem, we are performing image classification using a recurrent neural network. The layers that you set up now should be predictable and familiar to you. Here is our logits layer. It's simply a dense layer which has the number of outputs equal to the number of labels that we might predict. The input to our logits layer is simply the final state of our recurrent neural network. Once we have the logits layer set up, we pass it in to our cross entropy loss function. Remember, the cross entropy is typically used in classification because it finds the difference between two probability distributions, and this is what we want to minimize. The output of the softmax prediction layer is basically a bunch of probabilities, and the predicted label is the label which has the highest probability. The softmax activation is added to the logits layer using this tf.nn sparse softmax cross entropy with logits function. And from here on in, you should just be on autopilot when you're working with neural networks in TensorFlow. You calculate the loss, which is just a reduced mean on the cross entropy, set up the optimizer. Once again, we use the Adam optimizer and set up the training operation. The reason we use the Adam optimizer so often is because it's an adaptive learning rate algorithm and it requires very little tuning of the learning rate hyperparameter that you pass in. You can just use the default value, which is what we've done here, the default value being 0.001. This is what makes the Adam optimizer very easy to use. The predicted label is the one which has the highest probability output from our softmax prediction layer. tf.nn.in top k is what we use for this. We find the label with the highest probability because we are looking only in the top one label, that is the parameter 1 that is passed in. We then measure the accuracy of our prediction, again, something that we've seen before. Initialize all the variables that we set up in this TensorFlow program, and then prepare the test digits to be fed into the RNN. This involves reshaping the test digits to be the shape the RNN expects them to be. The batch size first, the number of steps or time instances second, and the dimensionality of each vector the third. Calling the reshape function on the tensor should accomplish this for you very easily. We'll run training for 10 epochs with a batch size of 150. We'll now run training on our recurrent neural network model. We instantiate a session. Again, as usual, we iterate through for every epoch, and for each epoch, we iterate over the batches. We feed in the MNIST training images to our recurrent neural network. Remember, reshape the digits in our training image before you feed it into the RNN. Run the training operation by using a feed dictionary to feed in the training images and the corresponding Y labels. Evaluate the accuracy on both the training data as well as the test data and print it out to screen. Go ahead, hit Shift Enter, and let the training process begin. And right away, within the first epoch, you can see the high training accuracy and test accuracy that we've received. This has two reasons. One is that RNNs work really well. Neural networks are great for this problem. Another is that the MNIST dataset is a simple dataset and it's easy for neural networks to identify patterns within this dataset. We end up with a test accuracy of 97.5, which is pretty good, especially considering that we've treated an image as sequential data before we fed it into the RNN. The training data that you pass into a recurrent neural network that has been built using the tf.nn.dynamic underscore RNN library function expects the input to be of a very specific shape. It expects a three-dimensional tensor where the first dimension is the batch size, the second dimension is the number of steps or the number of time instances for which the recurrent memory cell needs to be unrolled, and the third dimension is the vector size or the dimensionality of one input instance. Make sure that your data is in this format when you feed it into your recurrent neural network.